Okay, welcome to Lecture 14. We're going to talk about channel design and armoring. We're going to talk about riprap aprons and other channel armoring that we can do, and some different types of liners, both flexible and rigid liners for armoring streams. We'll talk about why we armor streams and how we can design channels for given flows and what flow velocities are appropriate for different systems. Lastly, we'll talk about the natural stream, or at least waterways that convey water, and kind of discuss the difference between threshold and alluvial type channels. Now, for next class, before you watch the next lecture or whatever for the next class period, make sure you review the NR 151 handout, and also please read Chapter 1 of the Wisconsin Stormwater Manual. In that lecture, I will allude to it. When you're watching it, you're going to need to fill out a sheet before you come to class, and you'll want to have read Chapter 1. It'll make filling out your sheet a lot easier. Okay, so let's talk a little bit about velocities exiting culverts. We talked about designing culverts. We kind of mentioned important things like aquatic organism passage or AOP and some other things. But here let's kind of get into the meat of, when we design culverts, there's some other things just besides preventing overtopping of a roadway or and meeting design flows that we should care about. One of them is that the exit velocities are typically higher than the discharge zone. The question is, well, why does this occur? Right? And so we'll look at that. But basically you can think, that we're constricting flow usually through a barrel that's a lot smaller than probably the natural channel width. So we're causing, if you just think in terms of Q equals VA, there's kind of your answer. So another question to think is, okay, well, what kind of design challenges does this pose? Who cares if it's coming out of the culvert fast? I don't care, right? Well, we'll see, that we do care for a number of reasons, both structural and those related to ecological systems. And then, we'll kind of, as we go through this, we'll propose solutions all related to the fact that we tend to increase velocities when we get out of culverts, right? So what do culverts do? Well, they effectively, basically, they channelize the flow for engineered conveyance. And so the cross-section area, it's probably reduced relative to what the actual cross-section of that stream area is. The slope tends to get increased over that short distance throughout that culvert flow, right? We tend to have steeper slopes than probably what would be in a natural channel. Obviously, the channel material has changed unless we're using a stream simulation type culvert, right? Now we're putting it through something that's probably got a very low Manning's end value, something that's very conducive to moving water through it, like corrugated metal or concrete. We've smoothed it out, we've taken out any of the rough stuff. We could also have plunging water coming out of this, which, unless we're in some sort of bedrock type environment where waterfalls might be a little more present in the stream network, we tend to not really see, plunging water from a stream because the slope tends to be more uniform. So let's talk about some of these design issues, right, as far as we're concerned, right? Basically, the normal velocities, they're too high. And if you look, this is kind of a neat thing that was put together. I think this was research done by Federal Highway Administration again. We've got a scour map where areas that are red show less scour, areas that are purple show increased scour. We've got flow coming this way, and you can see this is the inlet, and here's the outlet of our culvert. And you can see they measured this over time. Here's the bed level at the beginning of the experiment. This is that orange line here, elevation 0. And as flow is moved through this culvert over time, you can see that we start to get scour up at the head wall. So we could result in some structural instabilities here. But really, the big case is that we get a lot of scour downstream. And this isn't good for a number of reasons. It can basically undermine and cause structural issues with the entire embankment and culvert system itself. It could also cause this bed to erode away such that this culvert becomes a plunging system, which then really makes it not conducive to aquatic organism passage. So whenever we get these normal velocities that become too high, we tend to have no AOP. We've got scour immediately below the structure, and it can also create basically a choke or weak point for drainage and potential roadway vulnerability because we're not moving the flow through correctly. So what are some different solutions that we can do to this? Well, we can always change design, right? So we could change the design, and we've got some different variables that we know we could use to change in the design. We could change the slope of the culvert. We could obviously change the diameter of the culvert. And so here's a couple of interesting, here's an interesting figure, right? If we go from a 3-foot to a 4-foot change in culvert diameter, the percent reduction in outlet velocities 44%. So we've really reduced that outlet velocity by just going a foot bigger, right? And if you talk about going from 5 to 6 feet, now we've got kind of diminishing returns, but every increment that we go up, we're really reducing that velocity. And we know just from Q equals VA, right, that the area term has got a square in it, right? And so every time we kind of deal with changing that diameter, we're really reducing the velocity. And that could be a good thing. It could also be an expensive thing. So that's something that, or it could be something where we're constrained. We couldn't put a bigger diameter in there. So then we have to deal with some of these other variables, like changing the slope, shape of the culvert, or maybe even the inlet structure type, size, etc. Now, if we're really constrained and we can't really do much with any of these, as may be the case with many roadways, we can always use this other option here. We can armor the channel below the culvert. And so in the next lecture chunk, we'll talk about armoring culverts and some equations and nomographs that we can use to carry out calculations on how to design the riprap structure below it. And then we'll talk a little bit about a couple other tools, plunge pools, thrust blocks, and then that'll be the end of that lecture chunk, and then we'll kind of get into talking about threshold and alluvial channels and how we can design some other different types of linings for kind of long-term restabilization.